Alright, hi guys. This is Codeforces round 1107 Division 3. I will be participating virtually because I wasn't able to wake to go up to do this contest this morning. Um, yeah. Another thing, I'm started adding my sub count in my base IO template, and I will change it every time I do a recording of some sort. Yeah. So it would be nice seeing my progress. Um, Divide and conquer. You are given two positive integers x and y. You are allowed to perform following operation any number of times. Okay. Uh, if if y divide x, then it's possible. Good times good times. Good if it contains at most two distinct digits in its decimal representation. Uh, Find an integer y if both of the following conditions are satisfied. Y is good, x times y is good. Okay, so x is good, y is good, and x times y is good. Um, at most two distinct digits. Can you just can you choose y equals 10? If okay, so if you can add a zero, it's okay. 10, 11. At most two distinct digits. X has at most two distinct digits. Uh, so 732996767. If there are multiple valid answers, I'll output any one of them. I think integer at most two distinct digits. So if x, okay, so if x has two distinct digits and then you multiply it by y, um, y is 2, y 3, 4, 5. I think you can there's a always a valid y, right? There's always a valid y. Guarantee that x is good. And if x is good, so then it must be in like some form of a's and b's, right? So something like this. If you multiply this by you know what, you can just output 29 plus 1. Because so this is just one 9 times x. So x and then add 9 zeros. And then after the add one, you mean you add x to here. But the 9 zeros, there's 9 zeros and x is only to 1e8. Wait, yeah. Oh, y can only be the max y? What's the maximum? Okay. One, so 1e8 plus 1. 1, 2, 3, 4, 5, 6, 7, 8, so 1. Oh, there's zeros. Okay, so int d equals 0. Um, long curve. Here's equal to 1. Curve 1 is equal to 10. And I'll put plus. So it would be like x and x continuous. Okay. You have a binary string s consisting only of the characters 0 and 1. In one operation, you can choose the following. Choose a substring of s that is a palindrome of length at least 2. Delete exactly one character from this chosen substring. The remaining parts of the substring are then concatenated to form the new string s. Okay. Find the minimum possible length of the string s that can be achieved after applying this operation any number of times. Okay. Um, a pal. First off, we can reduce it to every single. Okay, so for every single consecutive value, you can change it. Yeah, int ll. The answer is either one or two. If it's 1010 or 0101, then the answer will be one. Otherwise, the answer is zero. I mean, otherwise the answer is two. Um, 1010. Okay, if the length, okay, int prev is zero or pre, int count is zero for car C S. Car pre will be S zero. Okay. Um, if C equals pre, continue. CNT plus plus, pre equals C, CNT. If yeah, CNT plus plus. If CNT equals one or CNT equals two or if CNT less than or equals to 3, let's see. Anything less than or equals to 3, if I can get to, let's see, if you have something like 10101010, because this is what we're gonna get. So what you can do is you delete the zero, you delete the zero, the zero, the zero, the zero, then you delete all the way here. Alright. And if there's an extra one, then you can delete and delete. And then 1. 1 is 1. 1, 0, 2. 1, 0, 1 is 1. So if the length, if CNT mod 2 is equal to 1, we can output 1. Otherwise, we can output 2. Uh, 1, 0, 1, 0. How do you, so 1, 1, 1, 1, 0, 1, 1. Any palindrome. So 1, 1 can be reduced to 1. 0, 1, 0. So over here, and we can take this away. And over here, and we can take this away. Right, and then over here we can take this 0. Okay, okay. Here's some number of ones, let's say. Is this 2? Is this always 2? Example 1, 0, 1, 0, 1, 0, 1, 0. So what we do is we go here. So we take the 0 away. We go here. So we take this 0 away. We go here. We take this 0 away. And then we take this 0 away. And then we can turn it into 1. Okay, so work 3. Oh, greater than which is 3. So only CNT equals 2, or it resign 2. Yeah. Um, yeah. In alternative way, you are given two arrays A and B, each of length n. You are allowed to perform the following operation on array A any number of times. Choose two indices L and R, and then for each index I from L to R inclusive. So it's alternating in its range. So basically you choose a range LR, and then for L all the way to R, we do -1, +1, -1, +1, and keep going on. No, it starts at +1. Yeah, +1, +1, -1, +1, -1, so on. Let me just reading the input. I feel like this is a greedy. So here, 1, 2, 3, 1, 2, 3. Is yes because so this is +1, and then this goes -1 as this goes +1. This is no because you can't go -1. This is yes. This is no. Go +1 minus. Okay, into ref. +1, so 2, 1, 2, 1, and then down. Ref, long for int I is 0 and I plus plus. If AI is greater than BI, ref minus equal to AI minus BI, else ref plus equal to BI minus AI. If pref is less than 0, I'll put no, return yes. Okay. I will explain the solution to the graded f later. Fair and square. A tree is an undirected connected graph of no cycles. For given a tree having n vertices, each vertex has an integer value ai written on it. For every two vertices, product of a value written versus line a unique simple path. UVW is called good only if that is a perfect square. Determine the number of good unordered triplets in the given tree. Okay, so um n seeing n vector int an or 0 is not 1 plus plus seeing AI, and we have a vector adjacency list. Well, so the first ones are all ones, and the answer is 10 because 5 choose 3. I should look at the second case. Okay. The second case, the answer is 48. Let's walk through it. If there's some nodes, so if you choose nodes 5, 4, and 6, right? Uh, 5 or 6 works because, okay, so 5 to 4, well, 5 times 4. See, let's look at the problem again. It's multiplying by the product of vertices, okay? So if there's like, we fix a root, and then we find two of its children, the product will be this one times, so 5 times 4 over here, and then 4 times 6, 6 times 4 times 5. So the root node gets counted twice. So if the root node has something like this, 2 times 10 to the 5. So the value of the root node has to be a perfect square. And then we can choose any, right? Yeah, any of its any of its sources. If we choose one, let's see. If we choose one and choose 8 and 4, then 8, 3, 4, 8, 3, 1, 4, 3, 1. Right, because one Uh, it's not direct. All three of those. So now technically 3 is the root node. So 3 is the root node. You can connect. So if 4 is the root, 4, we use 4 as the root node. We can choose any of the ones down here. Any of the ones down here. So 4, 5. So 4 can choose 5 and 6. Or 5 and 2, or 5 and 10. Or 5 and 7. With something up here. Or it can choose itself also. Okay, so the first thing, if it's a perfect square. So if it's a perfect square, then we can use it. Right? For example, let's calculate the answer for this. If we use node 1, then we choose something from top or just this, so it's 1. And then we choose any of our vertices down here. Is it any two though? It can't be any two. Has to be one of the in the subtree. So it has to go 1 here and then 1 over here. So we get 10 minus 2 plus 1 is 9. Okay. Uh, yeah. And then the next one is 4, and then the final is 9. So 4 we can choose 1, 2, 3, 4, 5. So we get 5. 5 times, so 1 and 4. Right, 1 and 4. So 4. That means 4 choices, right? Okay. So it goes 20. And then if we choose 9, so 9 doesn't have any other children, so we can't use it, right? Um, 2, 3, 4. So for 9, we can go 1 down here, 1 down here. I think if we choose to use node 4, um, if we choose to use node 4, for example, in this case, we can choose 2 from the top, right? 2 from the top, so 3, 3 times 6, something from the top, 18, 29 to 48. 1, you must choose node 9. If you choose node 9, choose like node 2 and 8. Then they would meet at node 3. So that would be the one counted most. If it's node 4, we can split into 1, 2, 3, 4, 1, and 1, 2, 3, 4. So we can split into 2 cases. Let's see. 1, use node 4. 4, 1, 4. So it's a pairwise product. So 4 times 1 is 4. 1 times 4 is 4. 8. 4 times 4 is 16, so 24. 2, don't use node 4. Then it's just 4 times 1 times 4 is 16. 40, and then for node 1, we have to use this node, and we use one of these nodes over here. So 10 times 2 is 8. Yeah. So, yeah, I think that's it. So we can use a DFS here. For every DFS, we need to keep track the size of the subtrees. So this will just be implementation details. Next equals par. Continue. Size curve. Plus just next. DFS. Right, next. Case 1 is use I. Case 2, don't use I. Case 1 use I. Vectoring. So these are all the possible choices of pause. For int next in adjacent S. I mean, current parent cur is equal to car in adjacent I. If next is equal to parent I, or just pi. Then pause the pushback n minus size of I, else pause the pushback size of next. If we so this might go to n squared. Okay, so we can use a map instead. Long answer 0 for auto pause. Let's convert it to a vector. Here int vc auto p vc. I mean in pause. vc dot pushback p dot second p dot. Do we need the first? Yeah, we need the first. Okay. Int m will be equal to vc dot size. For int I is 0, I smaller than m, I plus plus. For int j is equal to I plus 1, j smaller than m, j plus plus. Answer plus equal to vc I dot first times vc j dot second. Exponentation. Oh, this is just a value. We don't any steps this. You can choose any one of those. Okay. And it's vci dot first times second. or means I is 0, I smaller than m, I plus plus, answer plus equal to VC I dots. First times VC I dot first times VC I dot second times VC I dot second minus 1. And don't use I, it would be almost the same thing. VC I dot first times VC I dot second minus 1. And we add a king here. It's VC K dot first times VC K dot second. I won't add Glazing right now, I'm just gonna test it. So it didn't, oh, we didn't output anything, yeah. 38, 176, and 11. Well, we already used this side. Let's put to R, so like, basically it means the root. VC I dot first times VC first. Oh, can we just, choose something from over here, choose something from over here. There's no die. So for node 4, it would be 414. So it's 42, 1142. Um, yeah, 168. First. 214. Yeah, that's right. So first off, first one for a second. Let's get on. Oh, divide by 2. Divided by 2. Divided by 6. 24. right? 0, 0, 24. Oh, got to remove this. 35, 32, 8. So we're missing something? These two don't use R. We choose any 6 of those. I mean, choose any 3. Supposed to give 24. 24 plus 16, right? Don't use node 4. 0, okay. 24. So we didn't count this for some reason. More than M, J, K. Oh, because these triple. This is all 3 different. What if it has 2? New VC I dot first times VC I dot first times VC J dot first times second times VC at second minus 1 divided by 2, and we'll just add this over here, VCJ dot second. Okay, now all we have to do is change this to long longs. Accepted. What am I doing? Pop 200. That's pretty good. Oh yeah, 66 place. Okay. That was just plain math. We're probably F a bit odd. Alice and Bob have got a binary string as of length n. They have decided to play a game on it, taking turns alternately, with Alice moving first. In each move, the player must select a subsequence. Uh, Odd number inversions and deleter. The player who cannot make a move loses. Determine who wins the game, assuming both players play optimally. Okay. So inversions can only happen, in this case, is 1, 0. So 1 and then something 0, and we'll add it. So just Alice, higher string. And a 0 doesn't add any change. So 2 and then 1. And then this is wrong because this is 2, 2, 0. So Bob will win. I think if it has a even number of versions at the very beginning, well, like zeros can only go two. So C1 mod 2 is 1, or C1 mod 2 is equal to 0, and C1 is greater than or equal to. No, if it's 0, then after Alice takes one, Bob will always be able to take the remaining rest. Um, don't feel like this is correct. This is too simple for it. F. I'm gonna go get some water really quick. All right. Mm. Your passes compute sum of F over all the subbrace of A. Guess I'll try to solve. Each character of S is 0, 0, or 1. like subsequence has an odd number of versions and delete it. You can delete zero. Okay, you can delete 10, 1110. So on. Yeah, because I'm not. I don't really want to solve this problem because I have an idea, but probably I don't really want to implement it. I will go on with the solutions. I think 60 plays after like 45 minutes is pretty good, actually. So go on with the solutions. Um, Problem A, um, all you have to check if y can divide x. Because if y can divide x, you can just choose z to be x divided by y, and then you do x divided by z, and then you'll get y. So rather simple. But is it division three? So, for problem B, so what I did was, so okay, so for a number, any number, let's say 1, 2, 3, right? You can just multiply this by 1001, and you'll get 1, 2, 3, 1, 2, 3. Just to copy the number and then the number copied again. So you make the concatenate the number together. So basically, you find the length of this number. So the length L equals 3, and then over here you do 10 to the Lth power plus 1. So over here it will just be 10 to the third power plus 1, which is 1001. This works for any number because essentially, when multiplying, so having number x times 10 to the L plus 1, this is equal to x times 10 to the L plus x. 10 to the L gives L zeros at the end of x, and then add this x which has length L. There will be no more zeros left, and it will just be two x's together. So this is just what I did. While x, we just do curve times equals to 10, and x divided by equals to 10. I didn't use L, I just bought this 10 to the L instantly using this current, and output current plus 1. So yeah, a simple 2. I spent a little long on this though. Yeah, I spent a little long on this. It's correct. Problem C. Okay, yeah, problem C. So first of all, notice that if you have any adjacency of like zeros, for example, let's see, uh 0, 0, 0, 1, 1, 0, 0, 0. We'll just simplify this. We'll simplify this. So there's four zeros. This can be reduced to a single zero because 0, 0, 0, 0, you can reduce it to 0, 0, 0, which can be reduced to 0, 0, which can be reduced to 0. So this is becomes 0, and 1, 1, 1 becomes 1, and then it's 0, and then 1, and then 0, and then 1, and then 0, and then 1, and then 0, and 1, and 0, and 1, 0. Okay. So basically just simplify this, which is easily doable. After simplifying, we have some cases, right? So just assume that one is at the beginning. That one is at the start. Because if it's zero as at the start, we can just change the bits around and it will be the same thing. So if one is at the beginning, right? So the first case is length one. Then the answer is just one, right? If it's length two, then it has to be 1, 0. Then you just output two. If it's length three, you can remove the zero and then remove a one right after, so it's one. If it's length four, you can use these two zeros. How do I do it? Yeah, use this one to remove the zero, and then it becomes this case. So it's one, and then 1, 0, 1, 0, 1. You can use these three to remove this one, and then you'll become this case. So basically, it's a proof by induction. Starting from the length equals 3 all the way to length equals infinity, it will always be 1. Only if when length equals 2, the answer will be 2. So you find the length of the simplified portion, and then if length is 2, then you can output 2, otherwise it's output 1. Yeah, so let's see. And then so problem D, okay, so problem D, let's see how to explain this. Uh, okay. So note that, right, you can choose L equal R, and then this just means AL plus plus. So if AI is less than BI, you can always change AI to BI using L equals R, right? But is this always the best way? No. You can use L equals R or L equals R plus 1. Uh, L plus 1 equals R. So basically what I mean is, let's take, for example, this one, alright? So, first one, they're equal, so don't do anything. Now over here, AI is less than BI. So we add one to this and we subtract one to this. Um, we subtract one to this. Yeah. And then when we get to 2, 3, you can add one to this. And then we're done. Now, this might not seem very obvious why it works. So, let's see. How do I explain it? Okay. If AI is less than BI, right? It is, well, so first of all, because of this, right? Because we can do L plus plus for any value of A, it is always better to have smaller, because the smaller it is, the better chance it has of being smaller than BI. Smaller AI leads to better chance of yes, or just the same thing as um smaller than BI. Because we want it to be smaller. Smaller is better. So if it's smaller than it, we can just move AI to BI, and then we use AI plus 1. We subtract from AI plus 1. So now we have the formula. If AI, let's just shadow code if AI is smaller than BI, right? Um, AI can change to BI. Well, so AI plus 1 minus equals AI plus 1 minus AI minus AI. And AI can be changed to BI, but you don't really need this. Otherwise, it's equal to, yeah. Otherwise, out, but no. And then just for every I, for I from 1 to 0, output no, and then output yes. So Yeah, this is all we need. Oh, yeah, this code works also. But well, so what I did was I just used a prefix. So pre. So this is act just the number of times we use minus. So over here, instead of this, we'll just do ref plus equal to bi minus ai. Um, and then otherwise we do pref minus equal to. Well, actually, I think this code is simpler. So I'll just keep this code. Um, actually, I'm curious. Would that work compared to my code over here? Let's see. Minus equal to bi minus ai. A equals equal to bi. We don't need that. Else, see out. No. Return. See out. Yes. Oh, so it should just work. Yeah. We'll just. Is there a bug in my code? Why does it not work? I feel like it should work. The smaller it is, the better it is, right? Um. Oh, because it can go to long. Yeah. It can get too big. So long maybe. Should we use long? Will long work? Oh yeah, long works. Okay. So yeah, I think this is a better code than mine. So just look at this one. So it's this. Okay. Yeah. So now problem five. Okay, problem five is plain math. Yeah, this is just plain math. Um, graph editor. Okay. So we'll use this as an example. All right. So for any three nodes, let's say 1, 8, and 6. Now notice 8 gets counted twice because we have 8 to 1 and 8 to 6, so it counts twice. 1 gets counted twice, 6 counts twice, 4 is counted twice, 3 is counted 3 times. So actually, what this means is this node, the value of this node has to be a perfect square in order for D3 to work. In order for them to be, um, what's it called? In order for the set to be valid. Yeah, in order for the set to be valid. So, so what I did was I fixed this node, whatever this node would be. So let's just use 4 in this example, which is better than 1. If we use 4, so we count the sizes of these. So this is 4. There's 4 in here. There's 1 in here. There's 4 in here. So it would be 4, 1, 4, right? And then now you can choose to use this 4, or you can choose to not to use this 4. If you use this 4, then it's just choose two of the subtrees or subtrees. You can call them subtrees. So if you use two of the subtrees, then the answer will get 24 because it's 4 times 1 plus 4 times 4 plus 1 times 4 equals 24. Because 4 times 1, you can choose 4 from here and 1 from here, or 4 from here, 4 from here. I mean, one from these and 1 from these, 1 from these and 1 from these, or 1 from these and 1 from these. And then if you don't use node 4, it has to be choose 3 different subtrees. So 1 from here, 1 from here, 1 from here. So 4 times 1 times 4 equals 16. So yeah, that's just what you do. So for every node, if it's a perfect square, you can just do this. Um, well, notice, uh, in the worst case, a node can have n minus one children, right? So if it's just like node one, node one to two, one to three, one to four, one to five, one to six, one to seven. For example, like this, right? Every tree. Now notice this has n minus one nodes. So if we do this, so use node four, then it would be one times one, one times one, one times one, so on. That would be n squared. And don't use node four will be n to the third. But n is up to two times 10 to the five. So what I did was I stored them as a map. So basically over here, all this would just condense to a node of all of this. So three, we can remove three, four, five, six, and seven. And then node two would just have a weight of six, technically. Like the node is called node two, but it has an extra weight of six. Um, so six nodes in this subtree, technically. That's what it really means. So we do that. First we gotta use a DFS to calculate um parents of the nodes and the subtree size. And then so we use the map. Now I change it to a vector to make it easier. So M just means there's M subtrees. Okay, so now choose to use R. If we use AR here, okay. Um, so if we use AR, so let's say here we're using four. So we choose to use four. Um, currently the map, currently the map, so position will be four is two, one is one, and four is two. Uh, so the first case is if we use two of these or two of these, right? So this is just this. Um, the second case, if we use one from here and one from here, right? Let's say there's like something else like eight, four, and 10 and two, right? And we choose one from here, 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 and just so on. So this is m squared and this is m, right? And then if we don't use r, copy this here. So we can choose three from here, three from here, three from here, or three from here. So that's our first case. Second case is two from here, one from here, two from here, one from here, two, and then one, or it can also be one, two, one, two, one, two, and so on. So that's this case over here. These are not very important. They're more just a combinatorics. If you know combinatorics, this would go easy for you. And then final one is one, 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 uh, one, 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 and one, one, one. So these four. So this time complexity is m to the third power. So overall over here, max is m to the third. Max of m. Max of m is actually square root n because we use a position. So because we used map values at max will be keys at max will be square root n num keys, right? Because for example, if you have key of one, a subtree size, um, how do I explain this? Okay, uh, because let's say here's keys from 1 to M, right? Um, then the least number of nodes counted is 1 plus 2 plus dot 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 all the way to M. So which means the values are all 1. So there's only one subtree of each. Um, the least number of nodes counted is 1 plus 2 all the way to. Okay. This is M times M plus 1 divided by 2. Now notice that this is less than or equal to N. So complexity of M is square root. Now notice, so once M is square root of N, so total complexity is N to the 3 over 2 power. And then we multiply, so, and then outside over here, we have this, for every value, we take the square root and check if it's valid. Uh, since the square root is 10 to the 6, so for loop total complexity, we have a N times, uh, is the square root operating log time? Generally constant time. Uh, I'll just say it's log n, but it's probably just n actually. So n times, so this is probably O1. But so I'll just write log n plus this inside loop n to the 3 over 2. Now this will dominate. So final city is just n to the 3 over 2 power, which is n square root. And easily passable with n equals 10 to the 5th. Yeah, so this just, so we just used a we used a simplification over here using map. Uh, it speeds up everything from n third all the way to n to the 3 over 2. So we added a square root to it. Yeah, so this is E. So this is going to be my contest. I don't really want to do F. I don't feel like doing F. So yeah. Yeah, so this is just my contest today. It was alright. I did pretty good, I guess. I didn't do F yet because I don't want to, but yeah, sure. So, yep, I'm gonna post this, so bye.